Hey chemists, how you going? Just want to talk us through the results we obtained for our electrolysis design practical. So basically I've constructed a bit of a spreadsheet for you guys to utilize with your report. So I'm just going to talk you through what it is that we've done. So first of all, we've got our two practicals. So the first one up here, this is our independent variable of changing voltage. So if you're in that group, this is the data that you're looking at. And the second group down here was testing the effect of concentration on the copper sulfate electrolyte. So if that's your group, you'll be looking at this stuff down the bottom here. So I just want to go through what all this data is. So essentially we've got the voltages, which is what we changed. So we started at 0.51 and we went up to 3. So we've got trial 1 and trial 2. All of this data is what we inputted in the practical. So the initial mass of the cathode, the initial mass of the anode, weighing those copper anodes and cathodes, the final mass of the cathode and final of anode after removing and drying those. And then we had the current, the initial current and the final current. And I'll explain why we took those two measurements as we went. So now these two columns are formulas, and you can see if you click on individual squares, you can see the formula that's being used. So you can kind of figure out how I've worked all of these out by clicking on it and working backwards. So this is C5 take E5. So if we look at the cell, C5 is the initial anode and E5 is the final anode. So we're expecting the anode to decrease in mass over the course of the 5-minute electrolysis because the anode is where your oxidation happens, so your copper atoms turning into ions. Now, I've done this subtraction in the way that a reduction in mass leads to a positive result. And that's because on this graph over here, I want the change in mass of the anode to be a positive result, okay? So it's going to decrease in mass, but I've inversed the way that the subtraction happens, so it's seen as a positive result. So basically, this number here, 0.04, means that 0.04 grams of mass was lost from the anode, and that's reflected by a 0.04 positive number here. So that's symbolizing a decrease. The change in cathode mass is the opposite. Basically, that number is how much is being lost. So all of those should be positive because we've, sorry, my bad. The cathode is adding mass onto it, so we would expect that to be positive anyway, so the mass has gone up. So you can see if you look at your final cathode and your initial cathode, 28.54 to 28.57 is an increase of 0.03, so that is accurately reflected here, okay? Now, all of this stuff is to do with the actual theoretical calculations from our practical. So that's specified on the task sheet here. So that's saying how much copper should be electroplated. So these are the equations. So it's got to do with Faraday's first and second laws of electrolysis. And I won't read those. You can read those yourself. But this is how those laws are enacted in terms of theoretical calculations. So first of all, we talk about the charge. And to calculate charge, that's current multiplied by time. So I'll just go back to my spreadsheet and we can see that the current is averaged from the beginning to the end of the electrolysis. And we did that because we want to minimize the error associated with fluctuations of current. So the average current is just the difference between final and initial. Sorry, you add them up, divide by 2. So we took those two measurements. Basically, we have an average current over the course of the 5 minutes. Now that current is going to fluctuate, and that average might not best represent what it was throughout the whole 5 minutes, but that's a pretty good representation of our average current. So the charge is that multiplied by the time, so how long we had it on there for. So 300 seconds is 5 minutes. Then to calculate the moles of electrons or Faradays, that's the charge divided by 96500. Now what I've done there is actually calculated the number of electrons and then multiplied by Avogadro's number to get the number of moles of electrons. So that's going to be a very small number. Moving back, the moles of copper is the moles of electrons or Faradays divided by 2. And then to calculate the theoretical mass of copper that should be electroplated, it's the moles of copper multiplied by the relative atomic mass. So mass equals number of moles times molar mass. So I've got that here. So basically all of this is calculating this number here, which is the theoretical mass of copper being electroplated. And on these graphs, we see the blue line being the anode change in mass. We see the grey line being the theoretical mass of copper that should be electroplated. And then up the top, we see the cathode, which was the actual mass of copper electroplated onto that cathode. What we're expecting is all of those lines to be the same. So the theoretical, you can see that theoretical for this trial 1 here, it's quite linear. All right, we've got a few sources of error here that doesn't seem to match up with that linear trend, but it's pretty linear, okay? And we can see how different the anode and the cathode change is. Now that indicates quite a significant source of error, okay? And these percentages here are the correlation between anode and cathode. So how similar are the orange line compared to the blue line compared to the orange line, cathode and current, anode and current, and this is for the bottom here, okay? So the current is referring to that theoretical mass electroplated here, okay? So basically, this graph for trial 1 is telling us that there is pretty significant sources of error, both random and systematic, involved with this. Now, if I was analyzing this, I would be saying the fact that these don't match up means that I feel like maybe even if you look at cathode, that the mass of the cathode is all, in terms of the difference in mass, is always greater than theoretical. To me, that means maybe our drying process was not as effective as it could have been. And I noticed that throughout the prac, we were taking it from the copper sulfate and going straight to the air dryer when I was saying that we needed to rinse with distilled water to get that copper sulfate electrolyte off and then dry it. So I wonder if that has something to do with the fact that this is always consistently higher and this is always consistently lower, okay? So basically what this is saying here is we got more transfer from anode to cathode than what we actually expected by utilizing the theoretical equation. I wonder if that has something to do with, or as well, the fact that our electrodes were cylinders. So usually electrodes are solid without that hole in the middle. I wonder if that increase of surface area actually made us plate more than what we expected. So there's a few aspects we can consider, I guess. So look, if I'm going back to trial 2, the exact same thing. Look at the difference between trial 1 and trial 2. And then you might want to average those results out to create another graph to display. Look how different it looks. What does that tell us? I mean, the difference between the theoretical and the actual results here seems to be much less than in trial 1. So the difference between those two is random error. The difference between the orange and the blue to the grey, or even these two to each other, is systematic error, okay? So there's already some significant differences there between random and systematic. So for this group, the difference is minimal, so I won't go through all this stuff again, but we only measured one current here, but we've got our change in anode mass and our change in cathode mass. We would be expecting these to be positive again because the anode is always dropping in mass. Now this one here was negative, so that means that the anode increased in mass, which doesn't make sense because with electroplating the anode should be decreasing. And I put a note there, and that's because there was a deposit observed at the bottom. I remember this one where we had you could see that deposit forming at the bottom of the beaker. I took a photo of it. So that mass wasn't accounted for in our weighing. It was lost, but it wasn't plated on where it should have been. So perhaps that has something to do with that difference with that anode mass there. And also with our cathode as well, that wouldn't have been added onto the cathode either. So you can see in that graph here, it's expected that we're increasing over time, or actually based on our theoretical, that should be going up as well. So the fact that the theoretical is not going up means that there may be an error in terms of some aspect that we've made here, whether it was to do with the weighing. What else is incorporated into this? It's just the mass of the copper electroplated. The fact that this doesn't increase here, I wonder if there may have even just literally been a source of error where we're writing down what occurred. So it could literally just be an error with inputting the data. But regardless, you can kind of see with this one, there's a bit of a better correlation to the anode and cathode, which is good. There's a bit of a distance here, but this one's pretty spot on. This one's pretty spot on. So that's a good thing that they're so close together. But this is not expected. This should be going up, and the theoretical should be going up as well. This one, you can see the anode and the cathode, they correlate quite well also, but there's a significant difference between these two compared to the theoretical, when they should really all be the same. So if I'm looking at all of these graphs, they are all a bit different. The cathode is always higher than expected. The anode is always lower than expected. So there's something to do with our process in the practical that means we've got a source of systematic error where it's not lining up to where it should be. And we need to think about what that source might be. Okay, so I'm aware that this was a pretty long video, but I did want to just go through that data so you could make sense of it. You're welcome to use this data, but you'll need to take the relevant sections to your report. You can't just print screen this and put it on there, because it's not formatted in a way that we would include in our report. We need to have a results table. Now, most of this is useful and it can be used. You might need to produce another graph where you're taking the average of your two trials, or you will need to produce a graph. And then you'll need to analyze this data. So this kind of stuff, for example, I've got the working out up here. You can backtrack and use it, but you need to actually show the working out as per the task sheet in order to calculate that theoretical result and then include that in your graph. I've got the answers for you. You can check that you're doing it right, but you need to backtrack and show the working. Thanks, guys. Good luck with your report, and I'll see you later.